All right, guys. So we want to get going today. Again, picking up where we left off, section 1.2. We're going to jump into intercepts of a graph. So there it goes. Just as a reminder, again, I can't imagine this is anything that you haven't seen or picked up or noticed in the past. But when you are graphing, whether it's a linear function or you're graphing a quadratic, so like a parabola. You're graphing really anything, any type of function or any type of sketch. Doesn't even have to be a function. We have different numbers of intercepts that are potentially happening. And when we talk about intercepts, we're going to care about both x-intercepts and y-intercepts. So we have a situation, again, like this first one on the left. We can see that there's a y-intercept, but no x-intercepts. This other one, it looks like we have 3 x-intercepts, 1 y-intercept. Looks like this third one, we have 2 y-intercepts, 1 x-intercept, and then over here, the fourth final one, there are no intercepts of any type whatsoever. Now, if that circle on the furthest to the right, if that circle were just shifted differently, we could absolutely have an intercept or a few intercepts or a whole bunch of intercepts. Again, it's not necessarily a shape by shape thing. It's much more about a location thing. So I guess what I'm just trying to point out is that as we progress through here, it's possible to not have any intercepts. That's a very normal thing. It's also possible to have multiple intercepts. And when we talk about intercepts, once again, we are literally talking about where the sketch is crossing an axis. Is it crossing the x-axis here, here, and here? Those are your x-intercepts. Where is it crossing your y-axis? Okay, well, those are going to be your y-intercepts. One thing that we want to note here is that the x-intercept, it's going to be written with the ordered pair x, comma, 0. If you're talking about the y-intercept, it's going to be written 0, comma, y. So I'll just make a quick sketch down here. So if we were to think about something like this, trying to make something ridiculous, we would claim that if this were our sketch, that we have an x-intercept here, 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 and here. That's a whole bunch of x-intercepts. But each one of these are going to be written in a way such that, again, just making stuff up. Maybe this is like -9, 0. Maybe this is -4, 0. Maybe this is 1, 0. Maybe this is 3, 0, 4, 0, 6, 0, 10, 0. Hopefully we're picking up on the pattern that each one of these has a y-intercept of 0. That's kind of what makes it an intercept. I hope you would agree. If you think about what, structurally what it means to be a coordinate, like, again, when we claim that, yep, this is located at -9, 0, that means from the origin, we moved to the left 9 units horizontally, and then vertically, we did not move up or down at all. That's why we stayed on the x-axis. That's what makes it an x-intercept. So for that reason, if we have this line, it's referred to as the x-axis, we would identify that line as y equals 0, because any point on that line, the y value is going to equal 0. Now it's just the kind of the inverse to that idea, that concept, when we talk about any of the points that are y-intercepts. Any point that's on the y-axis, it's going to be x, comma, y, so 0, comma, whatever y is. Because from the origin, you did not move horizontally at all. You moved left or right 0 units, so 0 is going to be that x quantity each and every time. All right. Now, finding intercepts, that's going to be a little bit different story, but actually, the reason why we talk about what we just talked about is that we can actually use that concept in reverse. If we know that an x-intercept, we know absolutely that an x-intercept is going to be located at x, comma, 0, then why don't we just use the fact that we know that y is going to equal 0? Let's just use that, like I said, going in reverse, going backwards. So in order to find an x-intercept, all that we have to do is let y equal 0. That's it. Okay. In order to find a y-intercept, all that we have to do is just go the other way. We're going to let x equal 0. Okay. So it's quite literally a matter of just plug this in place and go to work. So here in our example, we want to find both the x and y-intercepts of the graph of y equals x cubed minus 4x. So should we do the easy one first? Yeah, let's do the easy one first. Let's find the y-intercept. Nice little delay here. So what that means is that we're going to let x equals 0. So if we were to rewrite our equation, we've got y equals x cubed minus 4x. We said that we're going to put what in place for x? 0 in place for x. So in cleaning this up pretty quickly, we're going to start to notice, well, 0 cubed is 0, minus, well, 4 times 0 is still 0. That just is telling us y-intercept is going to be at y equals 0. So it looks like the origin 0, 0. That's where the y-intercept is going to happen. A little bit more work is going to go into this next one. Theory is still the exact same, but if we have the x-intercept, what are we going to allow to happen? What are we going to let happen? We're going to let the y equal 0, exactly. So just like we did previously, you all saw me write that. Wait for it. There it goes. All right. So we've got y is equal to x cubed minus 4x. But in place for y, as we said, we're going to put a 0. So now our job, our task, is to solve for x. As you can see, it's going to be a little bit more involved than what we did previously. Looks like on the right side, we can factor an x out. That's going to be left with, or we are, I should say, are going to be left with x squared minus 4. Are we noticing anything about the x squared minus 4? Say that again, please. Difference of 2 squares. Again, depending on who your teacher was last year, the dots situation again might be something that we're noticing. Basically, we find the square root of x squared, x here, x here. We find the square root of 4 plus and minus 2. That's how we would factor this. If you'd like to factor it the more traditional way, that works as well, but that dots is a bit of a shortcut. So one of the nice things about math is that there are, I don't know, a few billion patterns that are all overlapping one another. This is very much one of those patterns. If you're multiplying numbers together, which I know that they don't quite look like it, but these are each numbers, x plus 2, x minus 2, those are just numbers, they're quantities. If you're multiplying things together and you get an answer of 0, that doesn't happen accidentally. One of those numbers at least, maybe all of them, are going to be 0. Does that make sense? So the way that we go about this, again, I know that you've done this countless times before, we set each of these equal to 0. So we have x equals 0, there's the first one. We have x plus 2 equals 0. When we solve, like x equals negative 2. Then we have x minus 2 equals 0. When we add the 2 over, x equals positive 2. Those would be our 3 x-intercepts. Bless you. Any questions? Now, obviously, this is kind of where we're stopping today, but we're going to pick up with this, and we're going to go a heck of a lot deeper with it. This is like chapter 2 of pre-calculus. We're going to do a whole lot more with this, just like you did a whole lot with this last year in Algebra 2. If we know that these are the intercepts, do you suppose we could draw a pretty accurate graph? Much more accurate graph now, for sure. Okay, and that's kind of where we go. All right, circles. Some of you had the opportunity to hear Will playing the circle song earlier as we were coming in. That was my first, hopefully last experience with the circle song. I've heard worse, I guess. No. But when we talk about the standard form of the equation of a circle, the fact of the matter is that a lot of students, again, who was the teacher? Mr. Daly, is that what you guys said? Okay. He's at Liberty? Okay. He probably talked about this circle song because people kept forgetting the pattern. They kept forgetting what the equation was. But this is absolutely one of those things that it's actually a lot simpler than you may initially think. Basically, what we have going is the center has to be located at HK. That's like inflexible. That's what I often call a non-negotiable. Like, that's not changing. Center point's at HK. So if we have a circle, wherever it is that we decide to put it. The center point, that's located, like we said, at HK. Well, we also have an infinite number of points that are on the outer edge of the circle. So maybe we have this point out here, and we call that XY. What do we call the distance from center out to the edge? Oh, that's the radius. Okay. Well, if we forgot about that for a second, forget that we called it a radius, forget that we called it anything. Do you suppose we know how, do we have a way of finding the distance between 2 points? The distance formula? As this is just the distance formula. That's all that it is. Okay? Now, it might not look like the distance formula, because we're used to seeing the distance formula like that, right? But I would imagine that somebody somewhere along the way said, I don't like that big radical, let's just square both sides. And as soon as you square both sides, and you stop calling it d for distance and said r for radius, that's the distance formula. That's all that it is. So again, if you're ever feeling a little shaky about what's the equation of the circle again, just remember you're just finding the distance between the center point and a point on the edge of the circle. That's all that it is. Okay? So if we're to try to pull that off here with the example that we have, center point is at 8, -3. So center is always hk, so now we know h, we know k. The radius is 4, so it looks like we know r as well. As soon as we know h, k, and r, it's quite literally just a substitution problem. We're going to plug everything we can into our equation. So we've got x minus, what did we say h was again, please? 8. Plus quantity, sorry. Y minus, what did we say k was again, please? -3. And what did we say r is, please? 4. So just a couple things that we need to clean up. We're good to go with this binomial of x minus 8 squared. But when we jump over here, the y minus -3, we could rewrite that as y plus 3 quantity squared. And then, of course, we want to square out the 4. So 4 squared is going to be 16. And this would be our equation. All right. Questions there? You see it? Feeling pretty confident with that? All right. So I'm going to stop this video. That's it for 1.2. I don't know what I did.